Hi guys, so I just wanted to show you today what some real batteries look like on the inside because like I said, this is like a larger scale of what goes on in there. And first of all, I actually made a mistake because when I was reading this, I wasn't paying attention to the fact that it specifically says positive ions there. Positive ions do flow in the same direction as the flow of electrons. They flow to the cathode. I thought, I don't know, I thought it just said ions in general, and I'm like, oh, well, they flow, one flows in one direction and one flows in the other, so they flow in both directions. So please make sure you understand that. If it specifies a charge, they do flow in specific directions. Okay, so this is the inside of a battery, and it doesn't look exactly like the picture we just labeled, but it has the same parts and the same thing goes on. We have a piece of zinc in here, and that's the anode. So we have oxidation of an active metal occurring. And then in the center of the battery, we have the cathode, which is graphite, and that's where the reduction is going to be occurring. So we have actually the negative side of the battery, because this is the anode right here, and we have the positive side of the battery, because that's the cathode right there. So electrons can flow through the battery from the anode to the without necessarily needing a wire. Now there's no salt bridge here because there aren't two beakers filled with solutions, but in the middle of the anode and the cathode we have this paste of MnO2, NH4Cl, and carbon. So that counts as our electrolyte that's going to help this process move along. Okay. If we look at this fuel cell right here, again, same thing, guys. This looks very different from the diagram that we labeled, but if you look closely, it has all of the same parts. We have an anode, we have a cathode, we have hydrogen being oxidized at the anode, we have oxygen being reduced at the cathode. So we're making hydrogen and oxygen ions together. They're making water, and they're making a lot of energy. Okay, we have electrons flowing from the anode to the cathode. So they all work in the same way, even though they might look a little bit different. So another way to determine if a reaction is spontaneous or not is to calculate the cell EMF. Basically, you're calculating the voltage based on the two metals that are in the battery, and if it's a positive number when you calculate it, it's spontaneous. Okay, so just to talk specifically about what a volt means, a volt is a unit for electricity, and it basically tells us how much energy it takes to move charges. Okay, that's what a volt tells us. So this table of standard reduction potentials, this is not on the Regents anymore, so this table is not in the reference tables, but you guys do have to know how to use it. First of all, these reactions are occurring under standard conditions, so that's important. For using this table, it has to be under standard conditions. And they're all compared to a reference reaction of hydrogen being reduced, where E is going to equal 0. Okay, so then all of these other half reactions or reduction half reactions were measured against that. So there's two ways you can go about calculating the E cell. You could either do the cathode minus the anode, which you'd have to like figure out which thing got reduced and which thing got oxidized, and make sure you do it in that order when you subtract. Or you can actually add them together like they're doing here, but flip the sign of the oxidation half reaction, because this table down here is only for reduction. So if any of these things were oxidized, the reaction would be flipped and the sign would be also. Okay, so let's just take an example. I have zinc here, being oxidized, 0 went up to +2, and I have copper being reduced. +2 went down to 0. So I want to go down to this table and I want to look for those reactions. So this is a very tiny table. Okay, here we go. I see copper +2 going down to copper 0. That's right there. And here's my zinc half reaction. Okay, so now if I think an ox met a big red cat, remember that sentence from the last video? If I wanted to do the first formula, which is E cell equals E of the cathode minus E of the anode, I have to figure out which one of these things is the cathode. So the cathode is the thing that got reduced. So copper in this reaction got reduced. So that would come first, 0.34. And I would have to subtract the anode. The anode is the thing that got oxidized. So that's a negative 0.76. So what do you get when you subtract a negative? You get a positive. So if I do 0.34 plus 0.76, I get 1.1 volts. And the fact that that's a positive number means that this is spontaneous. And you can actually double check that with table J. If you compare zinc and copper, zinc is the higher metal, so zinc should get oxidized, and it did. Now, if you feel like that was a lot to think through, what got oxidized, what got reduced, okay, well then what's the anode and what's the cathode? You can use the other formula where you just add the two together. But the thing that got oxidized, you have to remember to change its sign. So let's go back down and look. If I want to do the energy of the reduced thing plus energy of the oxidized thing. Okay, so now the copper got reduced. I want to leave that 0.34 positive. I'm going to add it to the thing that got oxidized. Now zinc has a negative 0.76. If I'm using this formula, I have to flip the sign because that's zinc's reduction sign. The oxidation would be positive. So I end up just adding two positive numbers together and getting the same answer. Okay? So you could either use table J or you can calculate E cell. If you get a positive number, it's spontaneous. If you get a negative number, it's not spontaneous. Anytime the question is regarding a voltaic cell, a battery, something that looks like this, you should always be prepared to get a positive sign because these do occur spontaneously. Okay? Have a good week, guys. We will finish this unit up next week. See you later.